Hey everyone, it's Freddie, and I'm going to be going over the second problem in this past January Gold contest. And the problem is called Lights Off. So in this problem, we are given two strings. The first string we can call the light string, and the second string we can call the switch string. So the light string represents a series of n lights, and the switch string represents a series of n switches, and n is up to 20. All right. And these strings are bit strings. So each of the positions is either 1 or 0. Okay. So if let's say the light string was 1001, this means that the first light is on. So if there's a 1, it means the light is on, and if there's 0, it means it's off. So in this string, the first and fourth lights are both on, and the second and third lights are off. Similarly, if the switch string was 1001, this would mean that the first and fourth switches are active, and the second and third switches are inactive. So Bessie's goal is to make the light string just 0, so to turn all the lights off. And she can do this using a series of moves, okay? And each move consists of 3 operations. So the first operation is to toggle exactly one switch, okay? So let's say the switch string was, again, 1001. Then she can toggle any of the 4 switches here. The first one, second one, third one, or fourth one. And this would just be flipping the bit of the corresponding switch. So if she wanted to toggle the first switch, then after doing that, it'd just be 0001. If you wanted to instead toggle the second switch, the string would be 1101. Okay, so she's just flipping the bit of the switch that she wants to choose. So there's n possible switches. So she can do n possible things in the first operation. And for the second operation, for each active switch, toggle the state of the corresponding light. Okay, so imagine, for example, that our light string, we're going to call it light string, is like 1001, and the switch string was like 0101. Okay, so for the second, if in the second operation we search for every single active switch, so the second switch and the fourth switch, and then we flip or we toggle the corresponding light. So in this case, this 0 would become a 1, and this 1 would become a 0. Okay, so the light string after the second operation would be 1100. And then the third operation is cyclically rotate the switches to the right by 1, which means, like, for this switch string, you just rotate like this. Okay, so it become the last bit would go to the first spot, so it become 1010. Okay, so that's the third operation, and all 3 of these operations together is a singular move. And so every single move has to do these exact 3 operations, no matter what. And Bessie wishes to know, what is the minimum number of moves to turn all the lights off? Okay. And the actual problem is asking, if we are given t instances of this problem, which means if we are given t light string switch string pairs, and where t is less than or equal to 2 times 10 to the 5th, can we output the answer to every single one of these pairs? Okay, so we might not just be given only one pair of lights and switches. We're given up to 10 to the 5th of them, and for each of these, we want to find the minimum number of moves necessary to turn the lights off. So let's do an example, or let's do the sample input to clarify the problem. So with sample input, t is 4, which means we're given 4 pairs of light switch strings, and n is 3, which means each of the strings will be length 3. So for the first, but this is a light string and switch string. For the first pair, the light string is 000, and the switch string is 101. So how many moves would it take to turn all the lights off? Well, the lights are already off, right? The light string is 0. So the number of moves it needs to take is 0 moves, right? Because we're already done. Cool. Now for the second pair, the light string is 101, and the switch string is 100. So how many moves would it take to turn all the lights off? Well, we can just toggle we can do it actually in one move. And for the first operation of the move, we toggle the third bit, or for the third switch. So the switch string becomes 101. And then we do the second operation on the light string. So for every single active, switch where there's two of them, the first and the third, we toggle the corresponding light states. So this, the light string becomes 0, 0, 0, and then we rotate the switch string, right? So it becomes 1, 1, 0. But the light's already off, which means we're done with that move, right? After that move, we are done. Cool. So the second input can be, or the second pair can be done in one move. For the third pair, the light string is 1, 1, 0, and the switch string is 0, 0, 0. Okay, cool. How many moves will it take to turn the lights off? Well, actually, the answer is 3, and we'll go over each of these moves. So for the first move, we toggle the first switch. So the switch string becomes 1, 0, 0, and then we search for all the active light switches, and we toggle the corresponding lights. So this becomes 0, and so the light string becomes 0, 1, 0, and then we rotate. So the switch string becomes right. We rotate the right by 1, it's moving like this way, and the switch string becomes 0, 1, 0. Now it seems like we are done, right? Because if we just did the second operation again on this would just turn the light string to be 0. However, remember, every single operation needs to have all three. Every single move needs to have all 3 operations. So we still have to toggle exactly 1 switch. So we're not done yet. So for the second move, the light string is 0, 1, 0, switch string is 0, 1, 0, L, then S. And the second move would just be to toggle the second switch. So it becomes 0, 0, 0. Okay. And then we find all active lights, or all active switches, and toggle their corresponding lights. Since the switch string is 0, 0, 0, that means there's no active switches, so the light string stays the same. So it's like this, and then we rotate the switch string, but since the switch string is all zeros, rotating it doesn't do anything. So after the second move, the light string is 0, 1, 0, and the switch string is 0, 0, 0. And for the third move, should be clear what we should do. We would toggle the second bit, right, the second switch, to become 0, 1, 0. And then after the operation, the light string becomes 0, 0, 0, and we rotate again, 0, 0, 0, 1. That means all the lights are off. So this took 3 moves. Cool. Now, for the fourth pair, all the lights are actually turned on. So the light string is all 1s, and the switch string is all 0s. So how many moves will this take? Surprisingly, this takes less moves than the last pair. It actually only takes 2 moves. So for the first move, we toggle the first switch. So this becomes 1, 0, 0. Then after doing the second operation, the light string becomes 0, 0, 1, 1, and rotating the switch string makes it 0, 1, 0. And the second operation, the second move, we toggle the third switch, so it becomes 0, 1, 1. And then after doing the second operation, the light string all 0s, and then we obviously rotate, which doesn't really matter since we've done. So it takes 2 moves. So that's the sample input. Now we try to figure out, okay, so how do we solve this problem? Well, immediately a brute force solution comes to mind, right? Because n is so small, n is only up to 20, right? This means that there are how many possible bit strings? 2 to the 20 possible bit strings, right? So maybe we can have a DP table of light and switch. So the first argument is the light string, and this can be represented as, right, a number, an integer, doing bit masks. And the second argument is just a switch string. All right, and the transitions are actually pretty straightforward, right? We can to figure out, so DP light switch will be the minimum number of moves needed to turn all the lights off, given that the switch string and light string are what the arguments are, right? And we can transition from the transitions, or just do all possible moves, right? So if we look at all these moves, each move, the second and the third operation are always like, we don't change anything about them. They're always just it has nothing to do with, we have no control over what they do, right? They always just do that. The only thing we have control over is the first operation, right? Because we can toggle any of the switches, right? And there are n possible switches, so we can do n possible different moves at each turn, right? So the DP transition would just be do all n possible moves and look at the DP states that result from them, and pick the minimum of those and make that our current DP state, right? And unfortunately, though, although this works, there's 2 to the n, right? 2 to the n, which is up to 2 to the 20 possible light switches or light strings, and 2 to the n possible switch strings. So there's 2 to the 2n possible DP states, and that is up to 2 to the 40 if n is 20, right? And 2 to the 40 is something like a quadrillion, right? So that's way too big. So unfortunately, this DP, this simple BitMath DP does not work. So we need to be a little smarter. And how do we do this? Well, we have to really understand what exactly is a move actually doing, right? Because all of this stuff seems very arbitrary, like especially the second and third, right, operations. Like we, for each active switch, toggle the state of the corresponding lights, and then cyclically rotate the switches to the right by 1. Like, what does that actually do? It's because it's very unintuitive when it does, right? It's like we don't really know what progress is, right? One of the light string and the switch string can be totally different one move, and after another move, it all rotates to be exactly the same thing, and then we turn all the lights off. So we need to understand what these what each operation is actually doing. So to do this, let's first look at the second operation. So for each active switch, toggle the state of the corresponding light. If toggle the corresponding light. So let's say an arbitrary switch is a 1, so it's active, right? And let's say its corresponding light was a 1. So what happens after the second operation? Well, since the switch is active, we toggle the state of the corresponding light, and this becomes 0, right? Let's say the switch was active, but the light was inactive. Then it's the opposite, right? Now let's say the switch was inactive, but the light was active. So since the switch is inactive, after the second operation, nothing happens to that light, right? So it becomes a 1. It stays a 1, right? And the last thing is, let's draw this over here, running out of space. Let's say the switch was inactive and the light was inactive, or light was off. Well, since the switch is inactive, we don't change the corresponding light state, so this just doesn't stay the same. So if you notice here, what does this output kind of look like? Well, if you guys are familiar with bitwise operations, this is actually the XOR, the bitwise XOR operation. Right? Because the bitwise XOR is defined as for inputs A and B, if A is 1, or if A is the same as B, then output is 0. If A is different than B, the output is 1. And this is exactly what this is, right? If these two things are the same, right, either zeros or ones, the output is 0. And if they're different, the output is 1. So the second operation is literally just the light string XOR the switch string. All right. So they basically use the sign light equals light XOR switch. Okay, that's the second operation. Now the first operation actually also pretty similar. So we can toggle exactly one of the n possible switches, right? And what does this toggling actually do? It's a bitwise operation. Well, let's say our light string was 1 0 0 0, right? And let's say we want to toggle the first switch. This is actually the same as XORing this with 1 bit shift 3. Which is actually 1 bit shift. This is the C++ bit shift operation. 1 bit shift, because 1 bit shift 3 is 1 0 0 0, by the way. So this would equal 0, which is exactly what we do if we toggled the first light switch. Oh, sorry, the first switch. This because so basically toggling the ith switch is equivalent to toggling the n minus I, or it's equivalent to XORing the string with 1 bit shift by n minus I. Okay, we can test this again. Let's say, so in this case n is 4, right? And let's say we want to target the toggle the fourth switch. So we would XOR this with 1 bit shift 4 minus 4 equals just 1 bit shift 0, which is 1. So 1 XOR, sorry, this is XOR 1 equals 1 0 0 1, which is exactly just toggling the fourth switch. Cool. So the first and the second operations are both bitwise XORing of some sort, right? This one's bitwise XORing of this shifted string, and this one is just bitwise XOR of light and switch. So it does seem, right, that the bitwise XOR is pretty prevalent in this problem. to maybe use some properties of bitwise XOR to solve it, right? And notice also that, let's say the third operation is not, it's unfortunately not really bitwise XOR, it's just cyclically rotating it. But we can notice that, like, let's say we wanted to cyclically rotate, right? So rotating seems to like completely throw off the string, right? However, it's not actually as bad as we think. Let's say our string was 101, right? And we toggled the let's say we toggled the first bit of the string, right? Or the first switch. So this is just XORing the string with 1 bit shift by 2, right? And then we rotate, then we did the third operation, right? We rotated the string. So this actually equals, right, 0, 0, 1. So we rotate it, the rotating, after rotation, it becomes 1, 0, 0. 1, 0, 0 actually just equals 1, 1, 0 XOR 1 bit shift by 1. So what is the relationship between this and this? Well, this first one is just rotating it to the right by 1, and this second one is just rotating this one to the right by 1, right? So actually rotation is just rotating this original string, and then you XOR something that the rotated version of the bit shifted thing. So if, and this applies regardless of however many moves we make, right? So if we wanted to, like, let's say we want to rotate this again, but we also shifted, like, this, let's say we toggled the second bit. So this is just XOR 1, or like, let's toggle, yeah, 1 XOR 1, right? 1 bit shift by 1. And we rotate again, this actually just equals, if we rotated this one, and we rotated this one, and we rotated this one, right? So this equals 0, 1, 1 XOR 1 bit shift by 0 XOR 1 bit shift by 0 again. So in order to do the third operation, all we do is keep rotating the original string, and then rotate all of the toggled bits, right? And if we did this one more time, this would actually wrap around, right? So this would become 1, 0, 1 XOR 1 bit shift by 3, or bit shift by 2, I guess. And then XOR again 1 bit shift by 2. Okay, cool. So rotations are actually not that bad, right? All we have to really figure out is rotating the string, and then we can just compute any of the moves, rotating them in constant time, right? We just keep shifting the bit over by 1. Cool. So now to really see how we can use XOR to solve this problem, let's do a more complicated example. Okay. Let me switch to my notes here. So let's say the light switch equals the light string is originally 1, 0, 1, 1, 1. And let's say the switch string was originally 1, 0, 0, 1, 0. Okay. So how many moves does it take to solve this? Well, the answer is actually 3, and we just work everything out. Okay, so for reference, I'm going to put the rotated version of the switch string. Okay, so after 0 rotations, this will become clear why I'm doing this later. So after 1 rotation, we just rotate, right? We take all the last bit and put it back, the first thing, and then for this, if there's 2 rotations, after 2 rotations, we take the last bit, right, and we put it back in the first, right? We just rotate it like this. All right, so this is just the original switch string rotated this many amount of times, right? 0, 1, or 2 times. Okay, so, and as we said before, right? We said before, this is very similar to light and switch. Okay, so after the first move I want to make is I want to flip the second switch. Okay, so after this, so we first toggle the second switch. So switch string becomes 1, 1, 0, 1, 0, which is, remember, as we said, toggling is the same thing as XORing, right? So this is actually just 1, 0, 0, 1, 0 XOR. This is bitwise XOR in like C++ and Java. 1, 0, 0, 1, 0 XOR 1 bit shift 3 times, right? These two numbers are equivalent. okay? And then we will toggle the light, right? Or then we do the second operation, which is XOR the light switch, right? Light equals light XOR switch. So basically this is XOR this number, okay? And then we shift the switch string to the right by 1. So then switch becomes, so after one move, after move 1, this is the resulting string. The light string is this. And the switch string is, so it's just rotating to the right by 1, right? 1 1 0 0 1 0 1 0 0 1 1 0 1, which is just this actually, right? One rotation, as we did before. We rotate this once and we XOR with the rotated one of the move that we made, right? So like this. So we shifted this one to the right by 1 and we shifted this one to the right by 1. Cool. Then we after this, so what is our second move that we want to make? Well, I claim that for the second move is to toggle the third switch, okay? So what would the switch string become? The switch string would become 0 1 0 0 1, right? Which is equal to this. To remove this, toggle the third switch. Third switch is there just 1 bit shift. So you XOR by 1 bit shift n minus 3. N minus 3. Which is just the same thing. This is, since n is 5 in this case, just this, okay? So it's actually the same thing as the first switch is right now, right? But that's kind of relevant. So the switch string becomes this, and the light. So light, right? Light is, right, for the second operation, we XOR the light with the switch string. So this one is this XOR this big string right here. So yes, the light string is becoming a little messy, but we'll reorder all of those terms later, and it would make sense why I did this. So this is, so after move 2, the light string is this, right? Okay. And the switch string, right, we rotate this entire thing by 1, right? So this one would just be, right, you take this out and you put it to the beginning. And this is actually just equal to this. XOR this, right? You shift all the things to the right by 1, like that. Okay, cool. So now we make our final move. So the final move is to just, toggle the first switch. Okay, so switch is this. So with toggling the first switch, just flipping that 1 to a 0, right? And this is equal to this, all right? XOR 1 again. So fourth switch, 1 XOR n minus, sorry, first switch, n minus 1. In this case, since n is 5, this is just 1 bit shift by 4, okay? So that's what it is. And then obviously we have to do the second operation, which is you XOR the light in the switch, right? And so you XOR this by this giant number. And if you work this out, this actually equals 0, okay? So this means we are done. So, I mean, we have a huge amount of terms here, right? We have like this light string becomes huge and it just equals 0. But let's rearrange these terms, okay? So here, so light equals this. So a very important property of XOR is the fact that XOR does not care about order. So A XOR B XOR C is the same thing as C XOR A XOR B, same thing as like B XOR A XOR C. I mean, it's the same, they're all the same thing, okay? So we can actually rearrange any of these, all these parentheses, right? All those parentheses around all the different terms, we can just remove them, right? So we can rearrange all of these, these terms exactly how we want. So this, I'll arrange it like or actually this is 0, 1, 1, 1. Oh, so sorry, this is 1, 0, 1, 1. Okay. So let's arrange, just put all these big bit strings in the front. Okay, so this equals 1, 0, 1, 1, 1, XOR 1, 0, 0, 1, 0, XOR 0, 1, 0, 0, 1, XOR 1, 0, 1, 0, 1, 0, and then let's just go down the line. XOR, let's do 1, 3, XOR 1, 2, XOR 1, 1, and then do this again. I'm just rearranging terms here. I'm not changing the string at all. And then, so these two equations, this one and this one, are exactly the same thing. I just rearranged them the terms. But now we have to make sense of what does this actually mean? Well, if you look at this, right, the first line, light is actually, I'm gonna make this equal to 0. Wait here, this equals 0, just for this to remember. All right, so this first line is equal to this is the original light string, right? Original light string. This is the original switch string. This is the original switch string rotated by 1, and this is the original switch string rotated by 2. This is not weird, right? And what is the second one? This second string equal to, right? It's the first move we made, right? So the first move, we XORed by 1 bit shift 3, and the second one we rotated, and then we rotated again. This actually turns out to be 0, 1, or 0, 0, sorry, 0, 1, 1, 1, 0, okay? And this thing is the second move we made, right? Is 0, 0, 1, 1, 0. And this is the third move we made, or this last line is the third move we made, 1, 0, 0, 0, 0, okay? So since the first move we made lasted 3 moves, right? That's why there's 3 1s in here in this string, in this resulting XORed string, right? Since the second move we made only lasted 2 moves, this way there's 2 1s, and the last move we made only lasted 1 move, right? Because we finished after the last move. So the string is 1, 0, 0. It only had 1, 1. Okay. Now notice that no matter what move we make, which 3 moves we made, the first line always stay the same, right? The first line never changes, right? It's not affected by any of the moves we made. The second, third, and fourth lines are the only ones that change depending on what move we made, right? So let's say instead we made, let's say instead of flipping the second switch for the first move, we flipped a different switch. Let's say we flipped the first switch, right? Then the light string at the end of the day, the light string would be like this. It'd be like this, and then instead of 1 XOR 3, it'd be 1 XOR 4, 3, and then 2. Okay. The only thing we change is just we're decreasing this. The same thing stays the same. These 2 lines stay the same. They're unaffected. If we just change the first move, this is what it would be. Unfortunately, this is not equal to 0. But yeah, it's just showing what happens when you make a different move. Like if we let's say instead of flipping the third switch on the second move, we flip the fourth switch. So this become this and this, right? And yeah, you can see what's happening here, right? Every move we make, we're just editing one of the rows, right? So this is very, very interesting because it means that we actually have a way of defining what a move is now, right? Because before it's all this rotation stuff, we actually know in order to turn all the lights off, this thing must equal 0, which means that, remember, if the bits are the same, right, for 2 numbers A and B, if you A XOR B, if A is the same as B, A XOR B is 0, okay? So our goal is now this. Our goal is just to make the first row above equal to the rest of the rows, right? If we make this first row equal to all these moves that would write all these other rows, then we're done. And we know that the first row doesn't change, right? If we make 5 moves, the first row, right, in this case we make 3 moves, right? No matter what 3 moves we make, the first row is the same. The only rows that change are the second, third, and fourth row, which are the moves that we're making. This could be like a DP, right? So like DP, basically we have, right, DP of moves left and masked. This means, right, this DP table takes in two arguments. First is how many moves do you have to make, right? How many moves left do you have to make? And the second one is what the mask that we are trying to make equal to 0, right? So in this case, we want to make this mask equal to 0. Okay. And yeah, so how are we going to be able to solve this DP? Well, right, at every single stage, we know exactly what the string would be if we made a certain move, right? So if we, for this case, if we had 3 moves left, the first move we make is going to be this row, right? So if we, and this equals, right, if we wanted to toggle the first switch, it would be this thing, right? If we want to toggle the second switch, I can just annotate here. So first switch, ooh, that's not good. The first switch, if we want to toggle the first switch, the bit string would be 1 bit shift 4 XOR 1 bit shift 3 XOR 1 bit shift 2, right? We want to toggle the second switch, similarly it'd be 1 bit shift 3 XOR 1 bit shift 2 XOR 1 bit shift 1. Want to toggle the third switch, this is very similar, right? And eventually, and these numbers, if you look at these numbers, equal this. The first switch is 1 1 1 0 0. The second switch is 0 1 1 1 0. Third switch is 0 0 1 1 1. Fourth switch is 0 0 0 1 1. Actually, this is a 1 here. 1 0 0 1, because they're being wrapped around, right? It wraps around after a while, and then it wraps around like this. If we want to toggle the last switch, it'd be 1 1 1 0 0, right? So all of these strings are very similar, right? They're just 3 ones just in every possible place in the string, right? The first, you start here, start here, start here, start here, start here, right? So all of the moves are actually very, very, very similar. And these are the only possible moves that we can do for the first row, right? And the second row is just if we decrement, right? The second row is if we just decrement the moves left by 1, right? So we can actually pre-compute all these possible strings, right? And on a side note, we will never need more than n moves to complete the or to turn all the lights off. And I'll leave that as like exercise. Why is that the case that we only need n moves? But yeah. So if this DP table, the moves left, as I said, is n. It's almost n, and the masks is 2 to the n, right? So how big is this DP table? N times 2 to the n is equal to around, right, with n is 20. 2 to the n is around 1 million, so it'll be like 20 million. So that's how big the DP table is, and this is within these space bounds. And note also that in this problem, we are given 4 seconds instead of 2 seconds, or I guess different for Java and Python, but we are given double the amount of time as we usually have. So we can afford to have like a slightly worse time complexity. So we can have a couple 100 million computations in total, or operations total, instead of, only restricted like 1 or 200 million. So if we make this DP transition fast enough, then we can solve it, do the DP table, right? We can construct the entire DP table. So we know that with a certain at a given moves left variable and certain mask, we know every single possible move that we can possibly make, right? And we can pre-compute all these. And I put these pre-computations in an array I call it placements. So placements takes two arguments, moves left, or moves, right? And then position, right? Like pause position. And basically it means like if we have this amount of moves left, what would the row be, right? Because in this case, if we had 3, the row would look like this. If we had 2 moves left, a row would look something like this. And if we had 1 move left, it would be like this, right? So computing this array is actually very simple. So you take a let me clear my annotations for a second. You take a bit string of length moves, right? So right, with the amount of moves we have left, we just a string of that many ones, right? Like that. If moves is 3, you just have 3. The string would have 3 ones, right? So we can start from any arbitrary thing and just rotate the string of ones around counterclockwise, right? And to do all the moves, right? In the example, In the example, when n was 5, right? When n was 5, n moves was 3. All of the moves were just 1, 1, 1, 0, 0, or 0, 1, 1, 1, 0, right? It's just rotating the string around, right? So to get all of these strings, we just have to first create a string with moves number of ones and then rotate it around n times. Okay, so a very easy way to get a string is we're gonna have like a variable called mask equals 1 bit shift moves minus 1. Okay, this is just a string with zeros followed by moves ones, right? Because for example, going back to the example, if moves was 5, if moves was 3, 1 bit shift 3 is 1, 0, 0, 0, and minus 1 is just 1, 1, 1, right? So 3 ones, and that's So it's a very simple way to do this. And then we just do this for I from, let's say, 0 to n, or 1 to n minus 1. Or yeah, I guess 1 to n minus 1 or 1 to n, doesn't matter. We just do placements, moves, I equals mask, and then we just rotate mask to the right, right? We just cyclically rotate it to the right. Or it doesn't even actually matter, to the right or to the left, it doesn't matter. We can choose to do this right. So how do we rotate a integer to the right? How do we rotate all the bits of an integer to the right? Well, you can do this pretty simply. Like, so when we're rotating it, right, we said we take the last bit and we put it all the way, we shift it all the way to the end. So this is just, if this is mask, so we do mask, first we divide it by 2, right? Because we have to take this, we divide it by 2. So we shift to the right by 1. It's like floor division, right? And we add, well, we add 1 bit shifted to n minus 1, right? And we only add this if the first bit was 1. So you just multiply this by mask bitwise and of 1 with 1, right? So this bitwise and with 1 just says, is there a 1 in the first bit? If so, then you add this this bit at the end. Otherwise, you don't. All right. So you do this like mask equals exactly what this is. Mask bit shift by 1 plus 1 bit shift n minus 1 times mask and 1. Okay. And this precomputes all the possible. So given a move, given the number of moves we have, this computes all possible positions we can toggle the bit, right? All n possible positions we can toggle the bit in the switch string. Cool. So we have this. Now we can compute the DP array. So the DP array goes like this. So first, what happens if DP 0 and then mask for some mask, right? So if we have 0 moves left, and also the DP will store, is it possible? So is it possible to make this mask equal to 0 with this amount of moves left, right? That's what the goal is, right? Is it possible to make this mask equal to 0, right? Using this amount of moves, and in this case, it's yes. But yeah, so zero mask. Well, it's only possible to make the mask equal to 0 with 0 moves left if, right? If, so this equals 1 if mask equals 0, right? Only if all the lights are already off, right? If mask is not equal to 0, that means we can't make the mask 0 with 0 moves, right? So mask DP 0 mask equals false. So I guess it's not 1. This is true, but true is 1 and false is 0 anyway in C++. But yeah, in other languages, you're just like DP mask 0 is true if mask is 0, and if mask is not equal to 0, DP 0 mask is false. Okay, so that's the base case. And I would do a transition, right? So for an arbitrary moves left and mask, how do you compute this? So we have to basically brute force it, right? We iterate through every single possible switch bit that we can toggle, which we know what the row is going to be, right? We know what this row is going to be. This row is going to be thanks to the placement, and we see if after toggling this bit, can we do it with 1 less moves left, right? And if we can, then we set it true, others is false. So so you initially set this equals false, and then you for I from 0 to n minus 1, or from 1 to n. If, right, DP moves left minus 1, right? So we decrement moves left, and then we do mask XOR, right? Placements moves left I equals true, then this is true, right? So this is basically, right, you toggle the bit and you edit the mask accordingly. And you said, is it possible to still do it with one less move, right? Because that we just use that move, and then the now we have one less move. Is this possible? Then we set it to true. Otherwise, right, if it's never possible, it will never be set to true, so it's false. So which means, right, because there's only n possible moves you can do. If all n of those results in not being able to do it, not being able to set that mask to 0, then we know that we can't do it. So DP moves left mask, it's false. So yeah, that's our DP. That's our DP table. What is the time complexity of this DP table? Well, of computing this DP table. Well, we know that there's right 2 to the n times n possible states in the DP, right? And for each state, right, we iterate through all possible moves that we make, right? All possible bits that we can toggle. So and there's n possible bits we can toggle. So multiply by n. So this is 2 to the n times n squared. Okay, which is around, and when it's 20, it's around 400 million computations. Like this, 400 million. I think that's 400 million. That's 40 million, 400 million. And since our time bounds were doubled, this actually works in the allocated time. So that's good. Now, how are we going to solve the problem using this DP array, right? So we need to go all the way back. So we know that like if and we can go back to the example case, right? Basically, we want so for this, this is equivalent to this problem doing this light and this switch is equivalent to saying is DP of this string sorry, DP of 3 this string true. Is this true? And it is true, right? Because we know we can do it in 3 moves, right? So basically, what we can do for every single query, every single one of these these pairs, we can iterate from 0 to n, right? And say, is it possible to make this mask 0 in n moves, right? So in this case, for this thing, we would be first we create DP 0 light or DP 0 light, right? So is it possible to do in 0 moves, which is only true if light is 0, right? And then we query, so this is not possible. Then we increment it, right? Is it possible to do this? Right? Is this possible? Or and then it's not possible, right? Is this possible? And then right, you XOR with the rotated switch, right? You XOR with this thing. And then this is not possible. And then we finally do, right, is this possible? And then you just rotate again, right? Right, is this possible? And the answer, this is actually true, right? So this is true. This is false. This is false. And since this is the first one that works, we know that the answer is 3. Okay. And if this is false, we keep going. So we keep rotating the switch, right? We keep rotating the switch string, and we think is it possible in the DP array, right? So how long does it take to answer each query? Well, it takes, right? I said it goes to n possible moves, right? Every string can be done in n moves. So it takes it takes n time O of n time to answer a query. So since we have up to n or 10 to the fifth 2 times 10 to the 5th queries, it takes 2 times 10 to the 5th times n, which is around like n is 20, so like 40 or 4 million. 4 million operations to answer all the queries, which is definitely within time bound. So we solved the problem. Done. I'll show you guys the code now, the actual code, because right, it's a little the bitmask DPs are always a little tricky to implement because we're just manipulating bits, right? All of these, right? What is it? All of these light and switch are all integers. They're not strings, right? Don't do strings because bitwise operations are very fast in the coding languages. So I always store these as integers, and we just manipulate the bits of the integer, right? So this actually, right, in this case, the light is actually just, I don't know, this is 7, it's like 16 plus 7, like 23 or something. And this is 16 plus 2 is 18, right? Those are the actual integers. And then, so we would actually just query like dp323, dp323 XOR 18, and it could, sorry, this would be 0, 23, 0, 1. But we wouldn't actually look at this. It would just be the integer corresponding with it. All right. So share my code here. So the code is very, very similar to what I said. It's actually pretty short. First we read it TNN, right? And then this is just computing the placements array, right? So right, we have a mask, which is initially 1, right, bit shifted to the right by moves -1. And then yeah, so then placements of this is mask. And then we iterate through every single possible, right, rotation, and we keep rotating, right? We keep rotating the mask, and we set that corresponding place in the placements to that mask, right? So now we have basically gotten all strings, or all possible rotations of a string with moves number of 1s in it, right? And then first we set, right, db00 is true, and all db0 mask, if mask is not 0, is false, right? Because with 0 moves, the only possible thing that you can do is if the light string was already 0. And then we have, okay, for moves left, right, for each possible move left and for each possible mask, we compute the DP, right? We do DP, right? So we iterate through all n, right? N possible different toggling bits we can do. And we check, right? If DP moves left -1 mask XOR placements moves left I is true. And if it is, that's good. And otherwise, this line is never going to be met, so it's going to be false. And if we query, right, this is just reading into the query, right? You see, I'm converting the string into an actual integer, right? Every single time we see a bit, which is 1, we just read it in the actual position of that bit. And this line is kind of unnecessary, but I just said if light is 0, we immediately return 0 because we already know it's done. Otherwise, right, we keep, so cur is my current mask, right? So first, like in the example we had before, it was the current starts out as just light, right? It starts out as just light. So just an example, which is 1, 0, 1, 1, I think, right? And then each time we try, can we actually in this case, this starts out as this XOR the switch, right? And then we check if it's possible to do this in one move, right? If DP of this, so this is possible. If not, which is not possible, right? Then we do DP of 2 of this thing, and then XOR this by rotating this one more time. I guess this is not this. This is 1, 0, 0, 1, 0. And then we XOR this by 0, 1, 0, 0, 1. And if not, then we again XOR by 1, 0, 1, 0, 0. And this is exactly what it's doing, right? So it keeps shifting, right? It keeps just shifting the switch to the right by 1. It keeps rotating to the right by 1. And then it XORs, right, your mask with that and keeps trying to query. And as soon as we hit, so as soon as this is true, right? As soon as we hit a true one, then we just print out the count, which is the number of moves we made, and we break, and then we're done. And this is the entire, pretty short actually, it's the entire code. Yeah, so that is the problem. It was a very interesting bitmask problem. I think these bitmask DP problems are becoming more common in Gold now. So it's very useful to know your bitwise operations, right? And also combine that with DP. So yeah, that is the entire problem for problem 2 for the Gold contest. Thanks everyone for listening.